Shall I start my presentation, sir?
Yes, ma'am. Yes, ma'am. You can just start.
It gives me immense pleasure to introduce resource person of this session, Dr. Deepak M. Sakate. He is Associate Professor and Head, Department of Statistics and Applied Mathematics, Central University of Tamil Nadu, Trivandrum, India. He is interested in developing statistical methods to identify necessary predictors for responses considered in various fields of research. As a principal investigator, he studied development of variable selection procedures in a zero and multiple inflated models for count data. He is interested in non-parametric tests for location, sale and location scale problem based on ranked set sampling scheme. He is actively engaged in developing methods for analyzing high dimensional data. He has designed and undertaken interdisciplinary studies in collaboration with scientists from other fields. He is an expert in data analysis using R software. He worked as assistant professor in Department of Statistics, Shivaji University, Kolhapur. He started his career as an assistant professor in Department of Statistics, Jalgaon. He did his bachelor's and master's as well as doctorate in statistics from Shivaji University, Kolhapur. He qualified CSIR NET conducted in the year 2008. Notable thing about this resource person is that while pursuing his MSc, he qualified these exams. He has also qualified ISS in November 2008. He was offered position of JTS officer, which is super class 1 post in Central Civil Services of Government of India. He visited USA as an exchange visitor for postdoctoral research at Development of Biostatistics and Epidemiology, Augusta University, Augusta, Georgia, in August 2015 and July 2016. He was actively involved in clinical studies related to dementia and obesity in American children. He is a life member of ISPS, IISA, and SUSTA. With this, I conclude my introduction and I request Dr. Deepak Sakti to deliver his lecture in this online one-week faculty development program under HRDC 2. Thank you, sir.
Thank you very much, madam, for a nice introduction. I am audible, right?
Yes, sir.
Okay. Let me share the screen first. Is my screen visible?
Yes, sir. Visible.
Okay. Let me first of all thank the organizers of this faculty development program, particularly SGM College, Karad, and HRDC Center, Pune University, for inviting me to deliver a talk on my favorite topic. I should say my pet topic. I did PhD on this, and even some research, extended research on these points. So thank you very much. Let me begin this session by introducing you people to a very applied and innovative way of putting your results in the form of certain models. These are actually called as regression models. But before actually getting introduced to regression models, I shall take you through some basic concepts of correlation, and then I shall introduce what is called as simple linear regression, and then we shall look in why we need multiple linear regression, and if time permits I shall also touch upon generalized linear models, which are kind of generalizations of this simple linear regression model. uh, I could see many known faces in the audience, and there may be some faculty members from statistics background. uh, Particularly those who are from statistics background, they may find this content to be elementary, but this is not for them. This is for those people who are not having statistics background. And I guess the faculty development program is general for this particular uh, event, and hence we can go ahead with the assumption that uh, the audience to this program is actually from a varied background. Let us begin with a situation wherein we are usually confronted with two variables or more than two variables. If we are having just one variable uh, and some data on that particular variable, then usually what we do is we go for uh, representing data on such a single variable using some descriptive statistics measures, particularly mean, median, mode, and so on. But when we have two or more variables, and if we just do individual variable analysis, then we may lose some information which is actually available amongst these variables. Say, for example, we are having two variables, and those two variables may be statistically dependent. If they are statistically dependent, and if we ignore that dependence, then basically we are losing some information which can be used for some better understanding of the phenomenon which has produced such type of data. So this presentation essentially is is going to motivate you people to look into the dependencies amongst variables, and then try to capture that dependency using some statistical model and use it for your betterment of research. So uh, let us imagine that we are having a situation. I shall go back and go one step ahead and explain one data, and then I shall again come back to what we are actually talking about. So basically, let us imagine a situation wherein we are having a banker who is interested to decide. We can say not just a banker. There could be somebody from a financing agency, because a loan can be provided not just by banks. There are some financing agencies as well. So in general, let me call it as a financing agency, and there is a concerned manager who is sanctioning the loans to the new customers, and he is already having some data about his existing customers for whom the loan was sanctioned. Imagine a particular product, say for example some home loan or any particular product. Okay, let us go ahead with home loan. So that fellow is actually responsible for assigning the rate of interest on a particular home loan for a particular customer. Now the question before him is like a new application is floated to him, and now he is ready to sanction that loan application, but he has to assign a specific rate of interest, which may be called as a lending rate in the language of commerce. If we are having some people having background from commerce, they may easily understand what I'm trying to say. So that lending rate is actually not fixed. You may see like banks or financing agencies, they are advertising that they are providing loan with so and so rate, but when a customer approaches, then rate of interest is fixed as per the financial status of that particular customer. So if we look at the situation of that manager, then he needs to know, or he needs to figure out what should be the lending rate for a new customer. As such, what he is provided with, he is provided with an application form from the new customer with all the necessary details about his financial status. If he look into his historical records, he could just figure out that he has been already available with lending rates and a debt to income ratio of some previous customers. So now immediately a question hits his mind, like whether this lending rate and debt to income ratio, are they related in some way? If they are related, then whether the strength of relationship is high. If the relationship, meaning strength of relationship, is high, then whether that relationship can be exploited further to develop a model which can be used to figure out what could be the lending rate given value of debt to income ratio. So he or she starts exploring the data, and you can see, like, just for sample I have given you some 10 observations on previous customers. So you can just read, like, this is the first customer for whom this was the lending rate assigned, and this was his debt to income ratio, and so on. And some summary statistics have been already reported, and I can understand that already you have been uh, listening to so many resource persons in this FDP, and somebody might have talked about these summary statistics as well. So the very first question which hits his mind, whether they are linearly related or not, and he just tries to figure it out whether it is happening or not. So he constructs a scatter plot. So scatter plot essentially provides a means of understanding whether a relationship exists or not. Relationship between two variables exists or not. So one variable is plotted on x-axis, the other one is plotted on y-axis, and you can see there could be possible patterns. This could be one of the pattern, which is showing kind of like a straight line passing through origin. Need not be always pass through origin, but it is showing something like a straight line, whereas this one is showing not a straight line but some curve. So we can call this pattern as a linear pattern, whereas this as a non-linear pattern. And in case of this linear pattern, basically we shall go ahead with this, and if time permits, then we shall talk about this as well. Okay, so let us assume for a particular setup, like linear relationship exists. In this particular case, it happens, and if we plot the data on lending rate and uh, debt to income ratio, it happens to be showing this type of pattern, which is essentially a linear pattern. So from this we can conclude, like for that particular problem, we can conclude that the relationship between uh, the lending rate and uh, debt to income ratio is linear. Now, having got some rough idea about the nature of relationship, can we establish or quantify the relationship? So quantification can be done using a measure of correlation. One can compute Carl Pearson's product moment correlation coefficient, or simply Carl Pearson's correlation coefficient. Okay, so Carl Pearson's correlation coefficient is a number which usually lies between -1 and 1, with 0 indicating that there is no statistical dependency, whereas anything which is close to +1 or -1 indicates that the variables are dependent on each other. You can say they are correlated with each other. Okay, so uh, in this case, if we work out the sample correlation coefficient, it happens to be 0.8253, and 0.8253 is a pretty large number as such, very close to 1. So one can conclude that there exists a positive relationship, we can say positive correlation amongst lending rate and debt to income ratio. It essentially means that higher the debt to income ratio, higher should be the lending rate. Okay, and so on. So now having got answer to the second question, the first question was whether the relationship exists, and answer is yes. Second question was whether it can be quantified, answer is yes. And the strength of the relationship is found by computing this number. This number is actually Carl Pearson's correlation coefficient. It can be found, meaning correlation can be found using some other ways also. It depends on the nature of variables. Here we are having only continuous variables, which can be thought of to be normally distributed. So use of Carl Pearson's correlation coefficient is advocated in such a situation. If we are having non-normal data, one can go for Spearman's rank correlation coefficient. If we are having binary data, then one can use Kendall's tau for computing correlation coefficient, and so on. So there are different versions or different ways of computing correlation depending on nature of data. So having got answer to the second question about quantification of the relationship, then the next thing is that whether this highly strong relationship can be whether it can be exploited to develop a model. And again, the answer to this question is yes, it can be done, and it can be done using mathematics along with statistics. So why I'm saying mathematics along with statistics? Carl Pearson's correlation coefficient indicates linear relationship. Okay, so we say we have a strong linear relationship. That means we can have a straight line which will cover almost entire data. Of course, it will not happen that all the data will fall on the straight line, but we can find a line which can be very close to almost all the data points. So we can develop a model which can be used instead of the data for further inference. Let us see what I essentially mean by this. So what I'm trying to say is it is a combination of both statistics as well as mathematics. The reason is the model is written in this way. You can see over here this yi is indicating your dependent variable. In statistics we call it as a response variable particularly, and xi is called as independent variable, and we have another name for this which is more popular. We call it as regressor or predictor. And b0 and b1, they are parameters of this model. They are constants, and y is actually a random variable. And this, if we consider model up to this part, we are actually talking about an equation of a straight line. And if we look at this term is actually indicating error. So in statistics we basically allow scope for error, and this error is not for measurement error, it is a random error which may get into the data. And hence we can see after plotting the data there is always a scope for like deviation from the line or deviation from the model. So whatever the model we are having, we are allowing some scope for error. Okay, so if we ignore this part, it becomes a mathematical model, just a straight line. If we put this, then we call it as a simple linear regression model. Why the word simple? Because only one regressor is included in this model. Only one independent variable is there. So b0 is actually called as your intercept, b1 is called as b1 is actually your slope. Okay, and as far as interpretation is concerned, your b1 is actually the rate of change in response per unit change in x. So if x is changed by 1 unit, your response y changes by b1 units in simple terms. And as far as this intercept is concerned, there is no much physical meaning, except like if your x is defined in such a way that it includes 0 as one of the possible value for x, then when we substitute x equals to 0, what we get is your intercept, of course ignoring your epsilon term. So it is just a mean of response when x is 0. That is what your b0 means. So as far as b0 is concerned, there is no much physical meaning is assigned to it. Only we need to bother more about b1. because this is going to decide whether your xi should be there in the model or not. I is actually indicating the observation. So here we are having n observations, so that we can put 1, 2, so on up to n. So this is a simple model which I would like to explore further for you people. So what I said was, like, correlation is there and one can easily quantify it, and after quantification one can see that a linear model can be built up. So because there is a relationship, we are trying to use that relationship to write an equation, because equation is going to help us. How? Let us see. Now, as far as this equation is concerned, there are certain assumptions which usually we people as user of statistics forget. We should not do that because they are very important, because validity of this model depends on it. So if assumptions are not valid for a particular data, model itself becomes invalid. And if it is invalid, your inference may be erroneous. And then some people start blaming statistics rather than looking into whether they checked whether or they validated the assumptions on the model or not. So statistics is kind of a toolbox. You can look at it from any angle. It is just a toolbox. Imagine, like, if you are driving a car and something goes wrong in your car, then what will you do? You will open the toolbox, or what if you call a mechanic, he will come with his own toolbox and he'll try to figure out what exactly is the problem. So what he will do, he will use spanners and all his tools to explore. So if he use a spanner in a wrong way, it will not open, meaning if the screw is actually concerned with, like, say number 10, and if he is applying number 12 spanner, then definitely it will not work. Same way with statistics. Wherever the data is satisfying the assumptions on the model can be used, and so on. So one should not blame the spanner, one should blame the user. That is how it goes. Anyway, so let us forget about it and come back to the assumptions on this linear regression. Linear regression model is actually assuming these things explicitly, and these two are hidden in the sense that they are, by writing this itself, it is very much clear, meaning we assume that the relationship between response and predictor is linear, so that we have written this model. Okay. And independent variable x is not random. So that is one thing. We fix x, we assume it as a control variable, and it is not going to change anyway. So what will change is only your response, meaning it will also change, but the changes, they are not random. Here they are random changes. And of course epsilon I is unobservable, so we will not have any observations on epsilon. So there are certain assumptions on epsilon, that on an average it should be 0. Then variance of epsilon should be a variance of error. We call it as error. It should be constant throughout all the observations, and error terms should be uncorrelated with themselves. And of course, the last assumption is very important. Epsilons, they should be normally distributed. So with these assumptions, this model can be applied for any given data with dependency amongst response and regressor. Say for example, in our case, wherein we had lending rate and debt to income ratio. So this is your lending rate, this is debt to income ratio. Then by some means you found out the estimates of the coefficients. Usually your B0 and B1, they are estimated from the data using a method of least squares, or you can go for method of maximum likelihood. Both coincide when you have epsilon, that is error distribution, to be normal. So you can just focus more on least squares, which is simple to understand, and incorporating less statistics, whereas in maximum likelihood estimation more statistics concepts are needed. But estimates coincide when we have error distribution to be normal, which is one of the assumptions as we saw in the previous slide. So by some software, if you are able to figure out what are the estimates, then you could have, like, the results displayed in this table. B0 is 0.258 and B1 is 0.774. Along with this, we can see there are some more things mentioned over here. One is standard error, other one is t statistic. One more column can be added which will indicate p value corresponding to these estimates, and you can also have some more columns which will indicate lower confidence limit for B0, upper confidence limit, and so on, which essentially constitute confidence intervals for these coefficients. Now, as far as that manager is concerned, he is actually uh, very much in need of such type of equation, because uh, he wants to figure out the lending rate. And if he knows the debt to income ratio for the new borrower for whom he has to sanction loan, so once he has sanctioned loan, if he just plugs in the value of debt to income ratio over here and do this computation, meaning if he just multiply it to this and add it to this, he will get the lending rate. So lending rate can be found using this equation. That is how we can use linear regression in real life. Okay. So we started with a problem, and we ended with the solution that for new customer he just needs to plug in the value of his debt to income ratio in this equation and find out. And after simplification, he will get the lending rate. Then of course that may be a crude number which he can approximate to some nearest number which the financing agency may agree upon, and then put it as a lending rate for the new customer. Problem solved for that particular manager. So see, regression can be used for problem solving in some senses. But as far as a researcher is concerned, the job is not done yet, because what we did is like we computed a model, but we need to assess whether model is good or not. That assessment should be done so as to validate our result, meaning whatever the output we have got, whatever the lending rate we can compute, to validate it we need to uh, check whether our fitted model is good or not, and that can be done using certain measures. A simple measure is to look at goodness of fit test, which is usually reported as an output in any statistical software. I shall show you how this can be done using MS Excel, so that you can easily implement it when you are doing some research work. So usually there is a F test which is obtained using residual sum of squares upon its degrees of freedom, and in the denominator, and regression sum of squares, let me put it as n minus k, and regression sum of squares, let me put it as SSR, divided by its degrees of freedom, depending on how many, usually this is k if we are having n minus k over here, and so on. And we usually look at the value of this f statistic and also corresponding p-value, and based on the p-value we decide whether fitted model is good or bad. Interpretation is like this: if p-value is less than 0.05, then we have strong evidence to say that model is good. If this p-value is greater than whatever the p-value we have got, if it is greater than this, then we can say that your model is not good, and so on. People usually don't bother about this p-value for f statistic. They directly jump upon what is called as r square, which is in terms of statistics particularly called as coefficient of determination. It is nothing but uh, a measure for again assessing the goodness of fit. I shall not get into the technicalities like what is variation and all, but as far as interpretation is concerned, I shall tell you that whatever the number you get as r square, that number indicates how much percentage of the variation in the response variable is explained by the model. See, statistical models are actually used for explaining the uncertainty, or we can say they are trying to capture the uncertainty in the data. So there is uncertainty. Uncertainty is measured using variance. And if y is having some variance, y is your response variable, how much amount of variance of y is explained by this model? That provides us a good idea about how good is your model. So R square in our case, in this example particularly, happens to be 0.6811, which is actually nothing but if you convert it into percentage by multiplying it to it by 100, it becomes 68.11%. So we can conclude that the model explains 68.11% of the total variation in response. The response was loan rate in that example particularly. Okay, some may be happy with this much explanation of variance. Some may feel, okay, only 68%, why not 80%, why not 90%? Some may even sit and say, no, I want it to be 100% only. If it is 100%, then no statistics is needed. So because that becomes almost sure, so variation is there, and variation cannot be captured entirely. We can think of like capturing it as far as possible, but entire variation cannot be captured. So anything greater than 0.5 in case of R square can be termed as good. Some may say that it depends on data also. Like some may like in current day scenario, if we are dealing with like lakhs of observations, then even R square of zero point 0.2 could be good enough. But if you are having just 10 observations, and if you get R square of R square say 0 0.2 or 0 0.3, then you should not be satisfied with that. You should look for a better R square. But how do we do that? I shall explain how can we improve the value of R square. So what exactly this R square is? This is the formula, 1 minus RSS upon TSS. RSS stands for residual sum of squares. TSS stands for total sum of squares. These can be computed. You don't need to bother about the computational part. Software does it for you. And yeah, one more thing. Unlike correlation, correlation lies between -1 and 1. R square lies between 0 and 1. So that one has to be careful enough to interpret. And as I already said, it can be interpreted as proportion of variation explained by the model. And yes, it increases with increasing number of regressors. This is what I just wanted to tell you. Larger the better, that is one thing. And of course, it increases with increasing number of regressors. If you go on adding regressors, R square will increase. But one has to be cautious while doing this, because this is an advantage as well as disadvantage. How? Advantage from one side, that most of the variation in the response is explained by adding additional variables into the model. But at the same time, this R square basically increases even if irrelevant variable is added to the model. Irrelevant in the sense it has no effect on response. When we are having y and x1 is already there, this is having effect on y. If we add x2 to the model, which is having no effect on y, R square will still increase, but contribution of x2 to the model is insignificant. So one has to be careful while adding extra variables to the model. We just need to check whether they are having effect on y or not. Then only they should be added. If they are added, your R square will improve, and so on. A good measure of percentage variation explained could be adjusted R square, which increases only when relevant variable is added to the model. If irrelevant variable is added, adjusted R square will not increase. Adjusted R square formula is little bit different than your R square. These quantities, they are divided by their respective degrees of freedom. Okay. And yeah, it always happen that your R square is less than or equals to adjusted R square is less than or equals to R square. Fine. So now, as I said, like in our case, we had R square to be say 0.68, and one may be wondering like whether this R square is not good enough. Then why shouldn't I add some more variables to my model? so that R square will be increased. This is naturally a good question, and one can explore this by having some more variables in the data. But then your simple linear regression model will not be useful. You need to extend it so that you can incorporate more number of variables into the model. That is done through multiple linear regression. It is actually of this type. You can write it as y is equals to, let me just use some Greek letters for denoting parameters of the model: beta 0, beta 1 x1 plus beta 2 x2 plus so on plus beta k xk plus epsilon. So this model is actually called as multiple linear regression model. Why multiple? We are having more than one regressors in the model. So we can see x1, x2, so on up to xk. Now they are actually denoting the variables, not the observations. I haven't put anywhere I in this equation. So this model is capable of handling more than one regressors, and it is commonly used for prediction. Meaning what? If the observation on this variable, and so on, all the variables are provided, then we can predict value for this variable. Fine. So again, how these parameters are found? These parameters are found by using method of least squares. And of course, this I already discussed. So method of least squares can be applied to find out the value of parameters. Yeah, so when I was talking about goodness of fit, I should also tell you, uh, like, after uh, knowing that your fitted model is good enough, one should not stop at that point. One should go one step ahead and check whether the assumptions made on the model, they are valid or not. So this is actually kind of a diagnostic procedure. These are computed for diagnostics, and I should say uh, they are actually doing validation of your assumptions on the model. Okay, so raw residuals are in simply, I shouldn't have put the adjective raw, because I'm not going to tell you. Maybe if time permits, if GLM is discussed, I guess it will not. Already 10:41. So in that case, if uh, you can simply call them as residuals. What are they? They are indicating the discrepancy of a fit. Meaning what? Meaning, if y is your observed response, or say yi, observed value, observed in the sense you have it in the data. From model, you computed yi hat, the predicted value for this y. So, how close this value is? You just take the subtraction and you denote it by ER. This becomes residual. Those from chemistry, they might be knowing the meaning of the word residual. Whatever remains after performing some reaction, okay, at the end, if you have some if you are harnessing some organic compound, if you do like A plus B, okay, and the result could be C plus D, where C is your desired product, you call it as yield. This is a byproduct which you don't desire, you call this as residual. Similarly, in regression, we are actually aiming at predicting yi as accurately as possible, but since it is a real life scenario, your predicted value will never coincide your observed value. Whatever discrepancy is left out, we call it as residual. In other language, we can say they can be called as remnants of a parameter estimation method. Whatever is left over, meaning it is left over, simply you can say it is a leftover, right? So they are actually used to uh, check or diagnose some problems in the regression model pertaining to validity of the assumptions. They are usually used in their some scaled form. Either they are used as standardized residuals or student typed residuals. I shall not put any formula for you. which will make you feel how complicated things are. So I shall just refrain myself not to put more equations on the screen. Anyway, now how one can validate the assumptions? As I said, normality is an important assumption because your entire inference depends on normality of the errors, and that can be validated or checked using normal probability plot. And this is usually found by plotting the residuals on a normal probability scale. Ideally, if this normal probability plot, if it happens to be a kind of an approximate straight line passing through origin, then we say that your model, whatever the errors we are having, they satisfy normality assumption. This is a graphical technique, and this may be subjective because a straight line is what we are going to figure out in our own mind. Okay, so uh, we never know whether the relationship is exact, meaning normal probability plot is really showing some uh, my video is on or not?
Not, sir, not.
Oh,
Screen sharing,
is going on, right?
yes, sir, is going on, but your video are not seen.
Okay. Now it
Yes,
is there.
yes, sir, yes.
Actually, what happened? I started sharing. I couldn't see the in the background. It was prompting me for giving permission to share my video.
Okay, sir, okay, sir.
Anyway,
It's
uh,
okay, sir.
just now I figured out that there is no light blinking on my laptop camera, so I thought like my video is not on. Okay, coming back to our discussion.
Okay, sir.
Normal probability plot, which I was talking about for checking the validity of normality assumption. Anyway, so if it is a straight line passing through origin, we conclude that errors are normally distributed. Any other pattern than this, you can say that normality is not there. I should recommend one more step. If you see that uh, you cannot figure out exactly whether it is normal or not, you go for a formal test of hypothesis on residuals, which could be like Shapiro-Wilk test or Anderson-Darling test or Kolmogorov-Smirnov test or chi-square test. Any of these tests can be applied to check whether distribution is normal or not. Then one can think of like a plot of residuals versus fitted values, which essentially gives you an idea whether error variance is constant or not, and of course whether the linear relationship which you have assumed is still linear or not. So plot of residual versus fitted values. What are these fitted values? These fitted values are actually found out by from the model, and when I write y I hat, uh, sorry, when I write y I hat, yes. So when I write y I hat, this is actually nothing but beta 0 hat plus beta 1 hat x. You can extend it for multiple linear regression. Just go on putting hats, and that becomes your y I hat. By hat, I mean it is the predicted or rather estimated value. So this value is called as your fitted value from the model. So we can plot residual against fitted values, and we can see whether there is a random scatter. If there is a random scatter which can be contained between two horizontal lines parallel to x-axis, we conclude that they are meaning there is no serious obvious model defect. But if it is not, if there is some pattern like inward opening funnel pattern or outward opening funnel pattern, or there is kind of a double bow pattern, all these patterns indicate that there is some non-constant variance. So constant variance assumption is not satisfied, so we again need to go back and recheck our model and then proceed. Yeah, the plot of residual versus regressors does the same thing. So these are two plots which are which can be interchangeably used for doing that validity of assumption of constant variance. Last one is actually plot of residual versus time or order. This plot is actually used to check whether your residuals are uh, uh, uncorrelated or not. And it is a very simple plot. All the residuals are plotted on the order scale. So on y-axis you have residuals, on x-axis you have order or time, meaning the index of this. You can simply put it as I. So e1, e2, so on. If there is a random scatter in this, then we say that error terms are uncorrelated. If there is a sinusoidal wave pattern like this, then we say that residuals are positively autocorrelated. So basically the assumption is not valid. If there is a random change in sign of residuals, random change in the, meaning a frequent change, like one is negative, then positive, negative, positive, negative, positive. This is origin. You can imagine like rapid change in sign. This may indicate presence of negative autocorrelation and so on. So problems can be identified using uh, these plots of residuals. And one more important aspect I would just like to tell you that as I told you, like if you go on adding variables to the model, it may happen that you are adding irrelevant variables. So whether variables are relevant or not, how do we identify? You can make use of variable selection criteria. Like you can go for, of course, adjusted R square or Malus CP, AIC and its variants, BIC, and so on. There are so many methods which you can apply to check whether added variables are relevant or not. For that, you need to compare two models, one with added variable, one without variable, meaning without added variables, and you can make a statement about the contribution of added variables to the model, whether it is significant or not. If it is significant, then you say that variables are relevant. If it is not, then you don't need to add them to the model. They become irrelevant variables. Then one may think, what happens if I don't bother about irrelevant variables? Let them be sit in the model. I don't care. Yes, the problem comes in the precision of your estimate. If you are keeping unnecessary or irrelevant variables in the model, the precision in estimated value will go down. So y hat will be less precise if it is based on relevant plus irrelevant variables. If it is based on only relevant variables, it will be highly precise. So we need to identify relevant variables and keep them in the model and discard the irrelevant one. This is popularly called as variable selection, and it is one of the important step in regression model building process. There could be situations wherein you may be confronted with a data which cannot be modeled using this linear regression setup, which I was talking about. Like I started with assuming that the relationship is linear, but what if the relationship itself is not linear? So in that case, what are the options? One option could be like if your response is binary one. For example, everybody might be watching some crime stories or movies based on crime or something. Just imagine a situation wherein a crime detective on a specific scene is encountered with a skeleton of a human being. Now by looking at the skeleton of human being, he cannot establish whether that skeleton is of a male or female. So gender cannot be identified from the skeleton just by looking at it. What can be done? Can statistics help? Yes, answer is there. So you can have your response as, okay, your response could be indicating 0. Say for example, these are just numbers. If the skeleton belongs to male, and if the one if it is female, for example. And you can have measurements on certain bones, particularly bones in the hip region. Okay, so bone lengths vary significantly uh, for a specific age group in males and females, meaning male human beings and female human beings. And the difference is statistically significant, which can be used to predict by using the bone measurements, whether the skeleton is belonging to or a skeleton is of a male human being or a female human being, and this can be done using again regression. But remember here, your response is not continuous. It is having just only two values, 0 and 1, and they may be repeated over say n number of skeletons, and we may have bone lengths say for a specific, say this is your leg bone, some hip bone, and so on, some bone measurements x1 x2 so on, say xk. So these may be continuous, but your response is not, and therefore your linear regression will not work. So you need to go for what is called as logistic regression. Logistic regression. So whenever you have a categorical variable as a response variable, you can still go for regression, but it is not simple linear regression or multiple linear regression. It should be something else. Even now, this was one case wherein you were having some binary type variable. You can have three categories also. In some example, there could be three categories, like your 0 may indicate cancer subtype. Okay, cancer subtype 1, some cancer subtype 2, cancer subtype 3, and so on. So for example, you may have three levels. In that case, you can go for multi-level logistic regression. Okay, now your response may represent a count of something, say count of occurrence of a specific event, say number of mistakes or number of goals scored by a particular football team in a World Cup league match. Okay, and so on. You can even put it as like number of times a particular person has scored a century in a world tournament, and so on, in a world cricket tournament, for example, and so on. So your response could be a count. If it is a count, this count cannot be negative, this cannot be less than 0. We are counting something, count cannot be -2, right? So if this cannot be negative, and this cannot assume any number between integers, like we are having 0 1 2 so on, a count of 0.5 doesn't make any sense. So normal distribution cannot be applied to such data, and therefore you cannot go for linear regression because assumption of normality will not be satisfied. So in this case, you can go for Poisson regression. There are so many varieties of regression models depending on the nature of your response variable. So blindly, I would suggest don't use any regression model for a data unless you know what exactly is the nature of your response variable. Quickly, I shall show you how this linear regression model can be implemented in Excel. So let me open Excel and let me open one data. Okay, so I am having this data in Excel. I guess you can see my screen, right?
Yes, sir. Yes, sir.
Okay, let me zoom it a little bit so that you can see the numbers clearly. Okay, now is it visible? Can you read the numbers?
Yes, sir. Yes, sir.
Okay, so y is my response variable. You can call it as a lending rate. X is your regressor variable. If you want to find out correlation between these two variables, you can just use COR command, CORREL, sorry, CORREL. In bracket, you give array 1. This is your array 1. You just click and select, comma, give array 2. This is your array 2. Complete the bracket, hit enter. You will get Carl Pearson's correlation coefficient. Okay, so this is your correlation. Can you mute the other participants? They are creating disturbance. Yes, thank you. So now if we want to construct a linear regression model for this data, we can do it from data option over here. In some systems, it may happen that this tab is not there because I shall be using data analysis toolbox. In that case, if this is not visible in your Excel, you can do one thing: go on Excel, click on this home button, Excel options. In Excel options, you can click on add-ins. It will show you the list. Now it is already in my active. In that case, in your case, if it is not showing in that ribbon, then it will be listed over here. So analysis tool pack. So what you have to do is you have to click on that. If this is below, you just imagine that the upper mentioned thing is below over here. So you can just click on this, and here you can click on go. Okay, manage Excel add-ins. Then it will show which are the add-ins available. Since this is already there in my Excel, it is showing tick mark. Okay, so if it is not there, then you have to just put a check mark on this. Okay, like this. Okay, checked, and then say okay. Then it will appear over here. Okay, so once it is there, then you can click on it. Then it will ask for certain options. Don't forget to scroll down because there are so many options below also. You can see so many things like ANOVA, one factor, ANOVA two factor, with replication, without, correlation, covariance, descriptive, statistics, and so on. So just scroll down and you will see regression. Okay, select it and click on OK. Then it will ask range for input. Okay, input range for y is your response. So you can select your y. I shall select from the top, indicating, yeah. So I should click on this labels because my selected range has labels. So labels and input x. So x. Okay, and you can see it is asking whether to include constant as 0. I will not. Okay, I am not forcing my regression equation to have 0 intercept, so I shall not click on this. If I click on this, it will produce me confidence interval with the level 95% for regression coefficients. And then here it is asking some output for like residuals and plots and so on. You can click whatever you need. Okay, and you can check out. I shall click on all these plots. Okay, now it is also asking for output range. You can just give an active cell over here somewhere, or you can have it on new worksheet also, no problem, and click on OK. And the moment sorry, it has taken something else here. Okay, output range here. Okay. Fine. So if I click on OK, it will produce the regression model. So you can see immediately it has produced. You can see certain things over here. Regression. Okay, you can see multiple R. It is actually correlation coefficient. Simply correlation coefficient. This is square, R square, multiple correlation coefficient. It should not be mentioned as multiple R. I don't know why it is putting it as that. It is simply correlation coefficient. Adjusted R square is this one. Standard error and so on. How many observations? 10. Now it is producing ANOVA. This ANOVA is actually for testing whether model is significant or not. You can see p-value to be lesser than 0.05, indicating that model is significant. Okay, so here you can go below. You can see coefficients. These are estimated coefficients, standard errors, their t statistics, and p-value, indicating that this intercept is insignificant, whereas coefficient corresponding to regressor X is significant. You can also see lower confidence limit, upper confidence limit for the corresponding regressors. Okay, and so on. Okay, it has produced additionally, by default it is producing these two things, and since I clicked on it and I didn't change the value for a level, it has produced the same thing again. You can have it as 90% over there. You'll get 95 as well as 90% confidence intervals. Since I clicked on residual output, it has produced the residuals like predicted y. These are predicted values. These are residuals, the discrepancy between observed and predicted, and these are scaled version of residual, and this is the data which is required to construct plot. Let us see whether plots are there. Yes, plots are also constructed already automatically. You can see normal probability plot, then line plot and residual plot. Of course, this normal probability plot is not in a good shape, so one should not go ahead with this particular normal probability plot, but rather you can use some other software like R to implement your linear regression model. Okay. Similarly, you can do it for multiple linear regression also. In that case, only X range will change. Let me quickly demonstrate to you. Okay, this data. I shall directly work out linear regression for this. We are having, you can see we are having 4 regressors, 1 response and regression. Okay, response. Let me select this. Regressors, this, labels, no confidence interval. Okay, I shall not ask for these things. And output range, yes, output range here. Okay, okay. So you can see immediately it has produced. Now you can see for this data, your R square is 0.98. Okay, multiple R square is 0.98, and you can see the coefficients and so on. Fine. Okay, so yeah, so that's all for the day. Thank you for patient listening. If you have any queries, you can ask.
Hello, participants. If you have any queries, please raise your hands.
Yeah, Rasik.
Hello, good morning, sir.
Rasik is yeah. Good morning.
Sir, in what cases the correlations and regressions are applicable?
Usually, whenever we are interested in assessing whether there is some relationship between variables, we go for correlation as an initial step. If correlation is strong, then we go for regression as well to use that dependency for prediction purpose.
Okay. Okay. Thank you, sir.
Okay.
Sir, no any hands raised, sir. So go for thanks. Vote of thanks.
Okay. Okay.
Okay, sir. Vidya Patil, madam. Hello. Unmute yourself. Yes, Patil, madam. Please.
Yes, sir. From a Monday, we have been enjoying intellectual feast in a one-week faculty development program. I take this opportunity to thank the resource person of this session, Dr. Deepak Sakate. He enlightened us through his deliberations on regression models. We are fortunate to listen to such a giant personality from the field of statistics. On behalf of SGM College Karad, sir, I express my heartfelt gratitude to you. I also thank all the delegates from various places for their active participation and patient listening. Thank you, one and all.
Thank you, sir. Thank you.
Thank you. Thank you. See you again.